The alarming acceleration of sea level rise is now clearer than ever, thanks to groundbreaking research using satellite laser ranging technology. But here's where it gets controversial. The exact drivers behind this surge are still debated, and new data is reshaping our understanding of climate change's impact on our oceans. Scientists from Kong Polytechnic University, PolyU, have unveiled the most precise 30-year record, 1993 to 2022, of global ocean mass changes, also known as barostatic sea level, using cutting-edge space geodetic methods. Their findings reveal that the increase in ocean mass is the primary force behind the rise in global mean sea level, GMSL, a key indicator of climate change's progression. According to their study, published in the prestigious Proceedings of the National Academy of Sciences, the global mean sea level has been climbing at an average pace of about 3.3 millimeters per year, with a noticeable acceleration in recent decades. This trend underscores the intensifying effects of climate change on our planet's oceans. To understand why sea levels are rising, it's important to know the two main contributors. First, the thermal expansion of seawater, which happens because oceans absorb roughly 90% of the excess heat trapped by greenhouse gases. And second, the increase in ocean mass caused by freshwater entering the seas from melting land ice, such as glaciers and ice sheets. Monitoring these changes over time is crucial for grasping the full picture of sea level rise. The research team, led by Professor Jianli Chen, Chair Professor of Space Geodesy and Earth Sciences at PolyU's Department of Land Surveying and Geoinformatics, LSGI, along with Dr. Yufeng Ni, Research Assistant Professor and lead author, achieved a milestone by directly measuring global ocean mass changes over 3 decades. They accomplished this by analyzing time-variable gravity field data obtained through satellite laser ranging, SLR, a technique that measures the distance between satellites and ground stations with laser pulses. Historically, scientists have depended on satellite altimetry to estimate sea level rise, while barostatic sea level data from satellite gravimetry only became available after the launch of the Gravity Recovery and Climate Experiment, GRACE. In 2002, SLR, although a traditional and highly accurate space geodetic method, faced limitations, such as a small number of satellites and ground stations, satellites orbiting at high altitudes, which restricts the resolution of gravitational data to large-scale features, and challenges in capturing detailed gravitational variations necessary for precise ocean mass estimates. To overcome these hurdles, the PolyU team developed an innovative forward modeling technique. This method cleverly addresses the spatial resolution constraints by integrating detailed geographic information about ocean-land boundaries, allowing for more accurate and long-term monitoring of global ocean mass changes. Their results show that between 1993 and 2022, the global average sea level rose by approximately 90 millimeters, around 3.5 inches, with about 60% of this increase directly linked to the growth in ocean mass. The researchers highlight that since roughly 2005, the rapid rise in ocean mass has been the dominant factor driving sea level rise, primarily due to accelerated melting of land ice, especially from Greenland's ice sheet. Over the entire study period, melting from polar ice sheets and mountain glaciers contributed to more than 80% of the total increase in ocean mass. Professor Chen emphasized, in recent decades, warming temperatures have sped up the loss of land ice, which now plays a leading role in global sea level rise. Our work provides the first direct quantification of this ocean mass increase and offers a thorough evaluation of its long-term effects on the sea level budget. This data is vital for validating climate models that predict future sea level scenarios. Dr. Ni added, "Our findings demonstrate that ocean mass changes derived from SLR data closely match total sea level changes observed by satellite altimeters, once thermal expansion effects are accounted for. This confirms that the traditional SLR technique, despite its earlier limitations, can now be a powerful and novel tool for studying long-term climate change. This research not only advances our scientific understanding, but also raises important questions. How should policymakers weigh the accelerating impact of land ice melt on sea level rise? Could reliance on traditional satellite methods have underestimated past ocean mass changes? And as new techniques emerge, how might our projections for future sea level rise evolve? We invite you to share your thoughts and join the conversation. Do you agree with these findings? Or do you see potential gaps that need further exploration?